the element that could have been crucial to the evolution of complex life on Earth. And scientists believe they found it. Oxygen, fundamental part of life on Earth, of course. After a surge in this gas in the atmosphere, roughly 2.5 billion years ago, multicellular life on our planet began to thrive, exploding with life. The timing is no coincidence, according to scientists, yet oxygen cannot take all the credit. According to some scientists, there's another element out there also crucial and needed to this evolutionary boom, and the name, of course, is iron. In a new review, Oxford University of Earth scientist John Wade and his team proposed that the metal's fluctuation helped to drive evolution on Earth. Today, iron is a necessary element for virtually all life, and it's what allows cells to sense oxygen, generate energy, replicate DNA, express genes, and there are only 2 known organisms on our planet that currently do not require this metal to survive. In the early days of Earth, there was plenty of geological iron to go around, especially in Earth's mantle and crust. The solid iron located here was probably seeded by meteorites from outer space, and because this material could dissolve into ancient oceans, iron was also abundant in the marine environment. After the Great Oxidation Event, GOE, conditions began to change though. Soluble iron began to grow scarce, and competition for iron among cells increased. Life forms in this way had to figure out how to recycle iron from dead cells, steal iron from living cells, or live in another cell and use the iron-grabbing apparatus to stay alive. And this was going over iron, or what some scientists believe first triggered multicellular evolution. Kindly support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box. The authors explain infection, predation, and endosymbiosis are all behaviors that switch the focus of iron acquisition from mineral sources to other life forms, and each of the 3 behaviors may evolve into others over time. For example, initially exploitation, infections may become mutually symbiotic. And compared to modern eukaryotes or multicellular organisms, older forms of single-celled life like bacteria and archaea are thought to have relied more on iron to survive. So this probably means modern organisms have learned to use the element of iron more efficiently over millions of years as its presence in the environment fluctuated. And according to this theory, Earth's oceans lost most of their soluble iron because of an increase in atmospheric oxygen. When water and solid iron interact in the presence of oxygen, the iron, of course, rapidly oxidizes, it rusts, which is a tougher for living things to make use of. To grab the element in this form requires cells to evolve small organic molecules called siderophores. Sidero meaning is from Greek word meaning iron. Today, almost all bacteria, plants, and fungi have these structures, but billions of years ago, this represented a new form of survival. And as life forms with siderophores began to gather near a limited number of iron-rich geological sources, researchers think crowding inevitably led to increasingly complex cell-to-cell interactions. Now, archaea in the thermal springs of Yellowstone supervolcano, for instance, can only really thrive on iron oxide mats, whereas modern eukaryotes can live outside of these geological sources as long as there are biological forms of iron available. The authors say, despite the depletion of bioavailable iron throughout the rebound of life post-GOE and its subsequent diversification and passage through other successive mass extinction events, iron has retained its preeminence in biological systems. They said, presumably this is because iron has a unique electrochemical properties that make possible or make efficient a range of biochemical processes such that other elements cannot be broadly substituted for iron within the proteins without causing a significant disadvantage. The sheer lack of replacement for iron means organisms either had to compete, cheat, or cooperate to survive following the GOE, and these developments could very well have caused extreme adaptations in genomes and cellular behavior over time. Now, when more recent neoproterozoic oxygenation event occurred, the neoproterozoic oxygenation event, about 500 million years ago, it merely exacerbated these changes. The initiation of terrestrial life may have started from an abundance of iron, but only when iron became scarce did those life forms begin to grow in complexity. Now, given that a rise in atmospheric carbon dioxide, CO2, could increase iron deficiency in the food chain, God forbid, researchers say we need to know more about how life copes with the ebbs and flows of this crucial element iron. The findings also indicate a possible way to measure the potential of life on other planets like Mars, where iron oxide can also be found in the mantle. If this planet is rich enough in iron, it could indicate a possible harbor for some of the simplest forms of life. This was published in PNAS. It's on Science Alert. The authors on PNAS says iron composition contributes also to water availability. The conditions of core mantle differentiation determine not only the mantle iron abundance, but also the abundance of other redox-sensitive transmission elements frequently utilized by life. These alloy-forming elements generally mirror the behavior of iron, such as when compared with Earth. The rocky portions of reduced planets like Mercury exhibit significant depletions in transition elements. The surface availability of elements that express redox-sensitive changes in speciation is greatly diminished, with S being the only likely abundant candidate. Now, this reduction in transition element abundance potential contributes to unfavorable conditions for the development of life, as incorporation of such elements in metalloproteins is critical for cellular biochemistry. Geology generates iron species relevant for biochemistry. The high availability of iron on the very early Earth was likely a key component in the synthesis of biological precursor molecules. It's been recently demonstrated that the close proximity of all three, ferric, ferrous, and native iron species, may be key in the abiological synthesis of a number of biological precursor molecules. The temporal evolution of iron bioavailability, given the abundance of both water-rich planetary bodies and life's elemental building blocks, it's likely that simple life is common in the universe. However, the Earth's transition to complex life, multicellular life, requires it to clear multiple environmental hurdles, not least those present in temporal changes in elemental abundance. So this is a very interesting thought. Please leave your comments. Thank you for your support.